Okay, guys, now we're going to do lesson 8 over composition of functions, day 2. Now we're going to use this table. The table is going to help us find values that we're needing. So we're doing, this is similar to what we did on the previous lesson. We're going to do 2 of f of g of 2. So first you have to figure out what g of 2 is. You go over here to where x is 2. Remember, this whole row here is the x's. And then from there, you go to where the g function is right here when x is 2, which is negative 3. So you're doing 2 of f of negative 3. We've just replaced the g of 2 with negative 3 because that's what g of 2 is. All right, erase all of this. So now we're going to add to that 3 of g of h of 0. So go here where our x is 0, and we go to where the h function is, and it's 3. So we'll be evaluating g of 3. All right, so now, using that information, we can do f of negative 3 and multiply it by 2. So f of negative 3 is negative 4. So we're doing 2 times negative 4 plus 3 times g of 3. G of 3 will be 2. So we get negative 8 plus 6, which gives us negative 2. All right, so next we're going to do h of g of negative 2. G of negative 2 is right here. It's negative 1. And you're going to multiply that times f of g of 2. G of 2 is negative 3. And then we're going to evaluate h of negative 1. H of negative 1 is 1.5. And we'll multiply that times f of negative 3, which is negative 4. And when you multiply that out, you get 6. Negative 6, my bad. Okay, the next question says, if k of x equals the absolute value of 3x minus 4, what values of x is k of x equal to f of g of 0? So f of g of 0... g of 0 is 1. So f of 1 is 4. So we want to know, when does k of x equal 4? So we want to know when does 4 equal the absolute value of 3x minus 4. And remember, when you're solving an absolute value problem, you want to get the absolute value bars off of that. So to do that, you break it up into 2 separate equations. So 3x minus 4 equals a positive 4, or 3x minus 4 equals a negative 4. And that's because whatever's under the absolute value can be positive or negative. The absolute value just makes it a positive 4. So whatever's inside of here could have been positive or negative. So solving that, we'll get 3x equals 8. Which means that x equals 8/3. Or here we get 3x equals 0, so x equals 0. So x could either be 0 or 8/3 to make the k of x equal to 4. Okay, next we're going to describe the transformations of the composition of functions given. So we're going to do f of g of x, which means we're plugging in the g function. We're going to be plugging into each of the x's x minus 1 into the f function. So you're taking this f function and you're plugging in x minus 1 for x, and then the f function wants you to square that. So this is our new function. Notice that you replaced your x with x minus 1. That means that you went to the right 1 unit. And that's what this graph would do. If you did x minus 1 squared, your vertex is right here at 1. And then you're going to have a parabola that just, it's been shifted to the right 1. All right, f of h of x. Into the x on the f function, you're going to be plugging in 2x. So you're replacing f of x and making it become f of 2 of x. So that means that you've got a horizontal compression by 1/2. But you can also see it another way, because if you do f of 2 of x, you'll be taking your f function and you're replacing the x with 2x. And you're squaring that, so that this is what f of 2x would equal. You'll square all of that, so that becomes 4x squared. So notice that's also a vertical stretch by 4. So a vertical stretch by 4 or a horizontal compression by 1/2 on that f of x function. G of f of x, that means that you're taking the g function and you're plugging in x squared. So into the g function, you're going to replace its x with x squared, and you're going to subtract 1 from it. So that transformation is basically that you're just squaring it. So that would end up giving you a parabola where it's been shifted down 1 from the original parent function of y equals x squared. All right, let's do another example. Okay, on this one, we're using these two different graphs. On this first one, we have our f of x equation, which looks like this. And then on our next one, oops, I don't know why that won't let me change. Okay, let's try that again. So we've got our f function that's right here. And then we've got our g function, which is right here. Okay, so f of negative 4. Remember, f is the pink one. F of negative 4 would be right here at negative 4. F of negative 3 will be right here at negative 2. F of negative 2 would be right here at 0. F of negative 1 is going to be up here at 2. F of 0 is 1. F of 1 is 0. F of 2 is 1. F of 3 is 2. And F of 4 is 3. All right, now let's do the g function. Let me erase all this, sorry. So the g function is using this one. All right, so g of negative 4 would be here at 2. G of negative 3 is right here at 1. G of negative 2 is 0. G of negative 1 is negative 1. G of 0 is negative 2. G of 1 is a negative 1.5. G of 2 is negative 1. G of 3 is negative 2. G of 4 is negative 3. All right, now that we're going to use this composite right here, we're doing f of g of x. So in this case, we're doing f of g of negative 4. Well, g of negative 4 is 2, so we're doing f of 2. And f of 2 is right here at 1. Or you could even look right here and get that 1 right there. All right, let me erase some of that. So next we're going to do f of g of negative 3. G of negative 3 is 1. So then we're doing f of 1, which is 0. F of 1 is going to be right here, which is going to give me 0. Let me erase all this so we can use it a little better. All right, on the next one, we've got f of g of negative 2. G of negative 2 is right here at 0, so we're doing f of 0. And f of 0 is going to be 1. All right. Next, we're going to do f of g of negative 1. G of negative 1, let me erase these on here. G of negative 1 would be, oops, not there. It's going to be right here at negative 1. And so then we're doing f of negative 1, and f of negative 1 is right here at 2. All right, next we were doing f of g of 0. G of 0 is right here at negative 2, so we're doing f of negative 2. And f of negative 2 is here at 0. All right, next we're doing f of g of 1. G of 1 is about negative 1.5. And then f of negative 1.5 is right here at 1. All right, next we'll do f of g of 2. G of 2 is right here at negative 1, so you're doing f of negative 1. F of negative 1 is here at 2. Next, we're doing f of g of 3. G of 3 is right here at negative 2, so you're doing f of negative 2. And f of negative 2 is right here at 0. All right, and lastly, we're doing f of g of 4. G of 4 is right here at negative 3. So f of negative 3 is going to be right here at negative 2. And then it wants me to graph that. So when x is negative 4, my h of x is 1. Negative 3, we're at 0. Negative 2, we're at 1. Negative 1, we're at 2. 0, I'm at 0. 1, I'm at 1. 2, I'm at 2. 3, I'm at 0. And 4, I'm at negative 2. All right. All right, next we're doing f of g of x and g of f of x. And then we were asked to find the domain of f of g. So f of g, that means into the f function, we're plugging the g function. So that will be whatever x is, which in this case would be the cube root of x plus 1. And then that gets cubed minus 1. So when you cube a cube root, you take the cube root off. So you have x plus 1 minus 1, which is x. And then we're going to do g of f, which means we plug in the f function into the g function. So you've got the cube root of plug in the f or the x. So it would be x cubed minus 1 plus 1. So that would be the cube root of x cubed, which is just x. Okay, so then they asked me to find the domain of this right here. When you find the domain, you look at what did you plug in, what's the domain of it, and then what's the domain of your result. So what I plugged in, into f, when I did f of g, I plugged in the g function. The g function is right here. So what makes x plus 1, think of what that graph looks like, the cube root of x plus 1. That's the cube root function that's been shifted to the left 1, so it's going to look something like this. And that's all real numbers for that. And then the domain for this right here would also be all real numbers. So my domain for this situation would be from negative infinity to infinity. All right, on the next one, when we do f of g, we're plugging in the g function into the x on the f function. So that'd be 1/3 times 3x plus 9 minus 3. Distribute the 1/3. We get x plus 3 minus that 3, which gives me x. And then I'm going to do g of f. It's supposed to be an open circle, sorry. Plugging in the f function into the g function. So the f function, it will be 3 times 1/3 x minus 3 plus 9. So distribute my 3. I get x minus 9 plus that 9, which gives me x. So again, I'm going to look at when I'm finding the domain of f of g, I'm going to look at what I plugged in first. So I'm going to look at the domain of this right here. Well, that's linear. It's going to be all real numbers. I'm also going to look at the domain of my result, which is also all real numbers. It's just y equals x. So my domain is from negative infinity to infinity. Okay, next we're going to do a situation where we have the volume of a weather balloon is given by this equation. If the radius is using this equation, the radius is in terms of time, the volume is in terms of the radius. We want to find the volume as a function of time. So we want to know V of R of T. So in my volume equation, I should have time instead of R. So everywhere I see an R, I'm going to replace it with what the R function is. So that'll be 4/3 pi. Instead of R, we're going to write what the R function is, which is 1/2 T cubed, and that's getting cubed as well. So then you've got 4/3 pi. You're going to cube all of this. So cubing 1, it's 1. Cubing 2, it's 8. Cubing T cubed would be T to the 9th because you multiply those two exponents. Multiply the fractions straight across, so you get 4/24 pi times that T to the 9th. 4/24 simplifies to be 1/6 pi T to the 9th, or you could write it as pi T to the 9th all over 6. All right, on the next one, we've got the number of bacteria in a container of leftover food stored in a refrigerator where T is the temperature of the food in degrees, can be modeled by this equation. This should have been a capital T right here. Sorry about that. When the container is removed from the refrigerator, the temperature is T of T equals 5T plus 3. It's specifically for this time period. So where the time is in T hours. So find the composite of this right here. So in this function, we're plugging in this function. So that'll be 60 times 5T plus 3 squared minus 140 times that 5T plus 3 plus 76. All right, I'm going to try to work this out real quick. So that ends up being, I'm going to write in this other part here, 60 times 5T plus 3 squared. That's like saying 5T plus 3 times 5T plus 3 minus 1. I'm going to go ahead and distribute this. 140 times 5 would be 700 T minus, let's see, 420 plus 76. Over here we've got 60 times, that'll be 25T squared, plus we'll do 15T and 15T, which is 30T, plus 3 times 3, which is 9. 420 plus 76. All right, now we've got distribute your 60. So 60 times 25 is 1500 T squared plus 1800 T plus 540. Okay, so next I'm going to simplify that. So that gives me, and I'm going to write it up here. Just erase all this. So that'll be N of T of T equals 1500 T squared. And then 1800 minus 700 is 1100 T. Oops, wrong T, sorry. Plus the 540 minus 420 would be 120, plus 76 would be 196, so plus 196. All right, so I'm going to erase all this again. So that's our equation for the number of bacteria with respect to time. This says find the number of bacteria in the food after the container has been sitting in out of the refrigerator for 2 hours. So N of T of 2 equals 1500 2 squared plus 1100 times 2 plus 196. So that's 4 times 1500, which would be 6,000, plus 200 plus 196. I feel like I've done something. Oh, this was supposed to be 1100. My bad. This should be 2200. So this adds up to be 8,396 bacteria. All right, so that's all of our notes for today. I hope that made some sense. Talk to y'all later. Bye.